we now discuss the solution of a problem from the section Sets, Relations and Functions. This given question is related to the concepts of invertible functions. This question has appeared in the Joint Entrance Examination Main held on 27th June 2022 in the second shift. The given question is, let S be a set consisting of the elements 1, 2, 3, 4, 5 up to 10. Define a function f from S to S as f of n is equal to 2n when n is equal to 1, 2, 3, 4, 5. F of n is equal to 2n minus 11 when n is equal to 6, 7, 8, 9, 10. Let G be a function from S to S such that f compose G of n is equal to n plus 1 if n is odd and is equal to n minus 1 if n is even. Then G of 10 multiplied by, in brackets, G of 1 plus G of 2 plus G of 3 plus G of 4 plus G of 5 is equal to. We are given a set S consisting of the elements 1, 2 up to 10. We are given a function from S to S defined like this. And we are also given a function G S to S. It is given such that f compose G of n is this one. Then required to find the value of G of 10 multiplied by, in brackets, G of 1 plus G of 2 plus G of 3 plus G of 4 plus G of 5. Let's now discuss the solution of the problem in detail. We have the set S consisting of the elements 1, 2, 3 up to 10. F is a function from S to S defined by f of n is equal to 2n if n is equal to 1, 2, 3, 4, 5. F of n is equal to 2n minus 11 if n is equal to 6, 7, 8, 9, 10. We are also given G, a function from S to S such that f compose G of n is equal to n plus 1 if n is odd. F compose G of n is equal to n minus 1 if when n is even. Required to find the value of G of 10 multiplied by, in brackets, G of 1 plus G of 2 plus G of 3 plus G of 4 plus G of 5. And to obtain this value, to obtain the above value, we need the action of G on S. That means the action of G on the elements of S. If we know, then we can do that. Now we are given f compose G of n is f of G of n is defined as n plus 1 when n is odd is equal to n minus 1 when n is even. Now, if in case f is invertible, that means if f inverse exists, then G of n will be f inverse of n plus 1, f inverse of n minus 1 on the respective values of n. So, if f inverse exists, that is if f is invertible, then G of n is equal to f inverse of n plus 1 when n is odd. G of n is equal to f inverse of n minus 1 when n is even. So, to find this value, G of 10 multiplied by G of 1 plus G of 2 etc. up to G of 5 plus G of 5. So, G of n is known when f inverse is known. Therefore, our first question is f invertible? If f is invertible, what is the action of f inverse on the elements of S? We have S. F is a mapping from S to S defined like this. So, if f of n is equal to 2n when n is equal to 1, 2, 3, 4, 5. When n is 1, f of 1 is 2, f of 2 is 4, f of 3 is 6, f of 4 is 8, f of 5 is 10. So, f maps 1, 2, 3, 4, 5 onto 2, 4, 6, 8, 10 respectively. Now, what this f will do? In the next case, 2n minus 11, when n is equal to 6, 2 6 are 12 minus 11, 1. 7 2s are 14 minus 11, 3. So F maps 6, 7, 8, 9, 10 onto 1, 3, 5, 7, 9. Agreed. Agreed. So we see that F is 1 to 1 and on to. How? F is mapping distinct elements of the domain onto the distinct elements of the range. The range is also S. Therefore, F is 1, 1. When F is 1, 1, F is a mapping from S to S. Both S and S are finite sets. F is 1 to 1, then it will be automatically on 2. So since F is 1 to 1 and F is a mapping from S to S where order of S is finite, then F is on 2. So F is 1, 1 and on 2. That means F is bijective. When F is bijective, F inverse exists. When F is bijective, F is invertible and F inverse exists. So now, from the action of the map F, F inverse can be guessed. So F inverse. Now, from the action of F, it is clear. F inverse maps 2, 4, 6, 8, 10 onto 1, 2, 3, 4, 5 respectively. And F inverse maps 1, 3, 5, 7, 9 onto 6, 7, 8, 9, 10 respectively. So from this, the action of F inverse is known on individual terms. But we want to know a formula for that. So from the first one, F inverse of 2 is 1, F inverse of 4 is 2, etc. F inverse of 10 is 5. We'll tell you F inverse of n is n by 2, where n belongs to 2, 4, 6, 8, 10. Similarly for the next one. What is that? For the second one, we'll show you. And we are very familiar with the method of finding the inverse of a bijective function. And we have F of n action and how F is mapping. We know, we have seen this one. Now F is invertible, therefore y is equal to f of x implies and implied by x is equal to f inverse of y. Yes, when f is invertible. Now take the first case. First case means 1, 2, 3, 4, 5 onto 2, 4, 6, 8, 10. So the first case is y is equal to f of x is equal to 2x, f of x is equal to 2x, when x belongs to the set 1, 2, 3, 4, 5. So when x belongs to the set consisting of 1, 2, 3, 4, 5, y will be 2x, means y will belong to 2, 4, 6, 8, 10. Y belongs to. So y is equal to 2x, then x will be y by 2. So what is x? X is f inverse y. So this will be f inverse y is equal to y by 2. For all y belongs to 2, 4, 6, 8, 10. So what's the action of f inverse? F inverse of n is n by 2. N belongs to 2, 4, 6, 8, 10. Okay, we got it. The next one. So y is equal to f of x is equal to 2x minus 11 when x belongs to the set consisting of 6, 7, 8, 9, 10. So note that x belongs to 6, 7, 8, 9, 10, then 2x minus 11, that is y belongs to 1, 3, 5, 7, 9. So this we have already seen. So y is equal to 2x minus 11. Solving for x, we will get y plus 11 by 2. So what is x? X is f inverse y. So this will imply f inverse y is equal to y plus 11 by 2, where y belongs to 1, 3, 5, 7, 9, the set. So the action of f inverse is f inverse of n is equal to n plus 11 by 2, where n belongs to 1, 3, 5, 7, 9. So now f inverse is completely known for us. F inverse of n is equal to n by 2 when n belongs to the set consisting of 2, 4, 6, 8, 10. And f inverse of n is equal to n plus 11 by 2 when n belongs to the set consisting of 1, 3, 5, 7, 9. So f inverse is known. So we will get g of n. Yeah, that we will do in the next slide. We have f inverse of n, and g of n we have seen in the first slide. G of n, f compose g of n is equal to n plus 1 when n is odd, is equal to n minus 1 when n is even. When f is invertible, then g of n will be f inverse of this respectively. This we have seen. So now, when n is odd, n plus 1 is even. When n plus 1 is even, what is f inverse? This is n plus 1 by 2. When n is even, n minus 1 is odd. When n is odd, n plus 11 by 2. So that means n minus 1 plus 11 by 2. The above one, n plus 1 by 2. So that will be equal to n plus 1 by 2 if n is odd, n minus 1 plus 11 by 2 if n is even. So n minus 1 plus 11 is n plus 10 by 2. So g of n, action of g of n is known now, n plus 1 by 2 if n is odd. G of n is equal to n plus 10 by 2 if n is even. So what is that we want? We want g of 10 multiplied by, in brackets, g of 1 plus g of 2 plus g of 3 plus g of 4 plus g of 5. So g of n is completely known. So g of 1 is odd, 1 plus 1 by 2, that is 1. G of 2 is even, 2 plus 10 by 2, that is 6. G of 3 is odd, 3 plus 1 by 2, that is 2. G of 4 is even, 4 plus 10 by 2, that is 7. G of 5 is odd, 5 plus 1 by 2, that is 3. And G of 10, so 10 is even, 10 plus 10 by 2, 20 by 2, that is 10. So all these elements are known now. So this will be equal to G of 10, that is 10, multiplied by G of 1 plus 6 plus 2 plus 7 plus 3. And in brackets, when you add, it is 19. 10 times of 19, that is 190. That is your answer. And that is the detailed discussion of the solution of a problem which is related to the invertible functions, and it is from the section sets, relations and functions. And to elaborate each and every step, we have taken more time, but otherwise it is very easy. Okay, I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.